Okay, so let me start with this uh, with this new topic, is in the Dirac equation itself. So far, I have been doing just Dirac equation of an electron, say. Okay? There is no coupling, but one has to introduce some coupling because electrons always interact with electromagnetic fields. So we need some prescription in order to understand what should be the form of this coupling. And since you have studied general relativity already, you can anticipate that in general relativity, the coupling with the gravitational field is essentially obtained by converting the ordinary derivative to a covariant derivative. Remember, because when you take ordinary derivative and study how it transforms under general coordinate transformation, or more esoteric language which is called diffeomorphism transformation, you find that it doesn't transform like a tensor. Okay? So you need to augment the derivative term with certain connection terms, affine connection or Christoffel connection, which will transform inhomogeneously under Lorentz transform, which by itself is not a tensor, so that the additional inhomogeneous term will cancel under coordinate transformation, any extra term that you get from the just ordinary derivative under this general coordinate transformation. So as a whole, the total object transforms as a tensor. This is just to remind you, you must have studied last year itself. Okay. Historically, of course, this was introduced way back in 1915 when Einstein finally placed his theory of general relativity and published it in 1915. But similar kind of situation was observed soon after that in the context of, say, Dirac equation and its coupling with the electromagnetic field. Same ideology has to be, or same principle is invoked there also. Okay. So let's try to see how this is done. Here also you'll see the ordinary derivative will not transform covariantly under certain transformation, which we call gauge transformation. And in order to ensure that it transforms covariantly, we have to modify the ordinary derivative term by a suitable connection term. And in this case, we will end up with this identification that this extra connection term is nothing but the so-called the vector potentials AMUs. So AMUs plays essentially the same analogous role as that of the Christoffel connection and affine connections. So geometrically, they are the same kind of objects. To understand the underlying mathematical structure which unifies this thing, you have to learn some more advanced level of differential geometry. If somebody is individually interested, I will be happy to say these things separately. But here I am not going to digress on these issues. Okay. So let me start with the Dirac equation. There used to be better quality chalks. There is no such chalk here. These chalks are not good. And let's see, try with this. This is a better chalk. So Dirac equation I wrote down earlier is I del slash minus m I of x. Just Dirac wave function is there, which is it? 4 component spinors, right? And del slash is nothing but gamma mu del mu. This is a shorthand notation, slash notation. Now you can see that this equation is, if you change psi x to psi prime x, is e to the power I alpha x alpha psi of x, where alpha is a constant, then I del slash minus m psi prime x also will be 0. Okay. So there is an arbitrariness of phase, and this phase is called a global phase because alpha is a constant. So this is called a global gauge transformation. And alpha, e to the power alpha, or alpha particularly, is called a global phase. Okay. Now, let me consider a transformation where make alpha a local function of x. Okay. Promote alpha to alpha of x. Make it a function of x. In this case, you call it local phase.
স্যার একটু বড় করে লিখবেন।
তোমরা এখানে অফলাইনে ক্লাস অ্যাটেন্ড করো না কেন? This becomes difficult for me to accommodate all the lines here. Okay. আচ্ছা, এই চকগুলো কিন্তু কোয়ালিটি ভালো নয়। এই চকগুলো ভালো কোয়ালিটির। এই চকগুলো। আর এগুলো কিন্তু খুব ডাস্ট হয়। আর মানে আপনি তফাৎ লিখে দেখুন, এই চক আর এই চক দেখবেন, আর এটা দেখুন, বুঝতে পারছেন তো? এই চকগুলো আপাতত আমার এই 2 চকেই চলে যাবে ক্লাসটা। নেক্সট ক্লাস থেকে এনশিওর করবেন এই চকগুলো যাতে থাকে। ওকে। So this alpha x is a local phase, and we can easily see that once you promote alpha from global to local phase, then this equation will no longer be satisfied. Okay, because I del slash minus m e to the power I alpha x psi x, where psi x is now mu psi prime x, is no longer equal to 0. Okay. So let me calculate these things. I del slash psi prime of x, I gamma mu del mu psi e to the power I alpha x psi x. Okay. Then you get I gamma mu del mu e to the power I alpha x psi x plus e to the power I alpha x del mu psi x. Okay. Now, this is simple algebra, So this will be I alpha x del mu alpha x to the power I alpha x psi x plus e to the power I alpha x del mu psi x. Okay. So as far as if you go back now, keep alpha x constant, then this term will vanish. Okay. So you go back to this thing. So if you combine this term, so it will have e to the power I alpha x I gamma mu del mu psi of x plus or minus gamma mu del mu of x psi x. So with alpha constant, this term will collapse and this phase will come out. Will ensure that this thing is just del slash. I can just write this as del slash. So it transforms covariantly, but this is extra term. Okay. Remember how does your Christoffel connection transforms? Gamma lambda mu nu under coordinate transformation. How does it transform? Gamma prime means under x mu going to x prime mu. Okay. If you make this coordinate transformation, gammas will transform. How will it transform? You remember? It will go to gamma prime lambda mu nu. First term will be like a tensor, right? Del x prime lambda del x alpha say, okay? And then del x beta del x prime mu del x gamma del x prime mu. Sorry, gamma beta gamma alpha. This is the first term. There will be another term. Del square xi lambda del xi lambda del x alpha del square x alpha del psi mu del psi. Sorry, I should not use xi. I should use prime here, x lambda. This means, right. Okay, something like this. So there is an inhomogeneous term. This term ensures that it transform. If in absence of this term, it ensures it transforms like a tensor. Okay, but these additional terms makes it a non-tensor. Similarly, here the derivative, this object up to this term is all right, but this term is additional term, which means that I have to need to modify this derivative operator occurring here to something like a covariant derivative. Okay, so so I modify covariant derivative. In general relativity, this is this is denoted by a comma, and this is denoted usually by a semicolon. Okay, it doesn't matter. Covariant derivative. So for covariant derivative, I write this is equal to del mu minus I some a mu connection term. Okay, and demand that d mu psi under transformation goes to both the d mu prime, d mu will go to d mu prime, psi will go to psi prime. This will transform as e to the power I alpha of x d mu psi. Okay, we demand that. So this demand, to fulfill this demand, you will see that there is, for d mu psi you write like this, d mu prime differs from d mu just by the derivative part will be same, but this part will be a mu prime. Okay, this d mu prime is del mu minus I a mu prime. Okay. So you can check this thing. And once you demand, you will get, I leave it as a homework. A mu will find that a mu has to also change, or if you want, I can do it for you. Maybe that will be better. So I demand this. So I have del mu minus I a mu prime psi prime. Psi prime is e to the power I alpha x psi x. Okay. And this should be equal to e to the power I alpha x d mu psi. So del mu psi minus I a mu psi. Okay. So what do you get? Let me erase this thing. So del mu acting on this thing that I have already calculated. Okay, I gamma mu, so it has this structure. Okay, so I del mu alpha of x e to the power I alpha x psi x plus e to the power I alpha x del mu psi x. Okay, this part I have already calculated, del mu of these things minus I a mu prime of these things e to the power I alpha x psi x. Okay, and this should be equal to, by demand, this is equal to e to the power I alpha x del mu psi minus I a mu psi. Okay, so you see this term e to the power I alpha x del mu psi, this cancels from left and right hand side. Okay, so you cancel. Okay, del mu psi, there is another factor of e to the power I alpha x. Okay, that I have missed, minus I a mu. And you cancel these phases also. This. So what you get? You get these terms are already gone. So I del mu alpha x psi x, even psi x you can forget, minus I a mu prime, psi x you can forget, and this is equal to minus I a mu. Okay. So now you forget, multiply both sides by I. So this will become minus del mu alpha of x plus a mu prime is equal to a mu. In other words, a mu prime will be a mu plus del mu of alpha. So you see, this is the thing. Okay. So a mu prime will transform like this. So this is the compensating term. Psi is transforming by itself covariantly. কিন্তু যখন ডেরিভেটিভ নিচ্ছ, গ্লোবাল ফেজ ট্রান্সফরমেশন, হ্যাঁ 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 রাইট। আমি দেখলাম এ মিউটা এরকম, and this is well known gauge transformation in electrodynamics. F mu nu will remain invariant under this. So this gauge transformation will recover from simple gauge principle, that your Dirac equation should be covariant under this local gauge transformation, and this gauge transformation is what is associated with the group. In this case, group is U1 group, isn't it? E to the power I theta is a U1 group element. Only thing is that this group is defined from point to point. So you say that you are gauging the U1 group. This is called gauging a global group. Earlier it was e to the power alpha, alpha was constant. It is a global U1 group symmetry. But now you have gauged it, that means you make it local, and in the process you have gauged the local global symmetry to a local symmetry. The global U1 symmetry has been promoted to local U1 symmetry. Okay. You can in fact do it. This group is abelian, you remember. You can do it for the non-abelian group also, SU2, SU3 and things like that. In this case, you will get more generalized structure. In this case, the gauge field A mu is called gauge field or the vector potential of electrodynamics. So Maxwell's theory you can identify with the U1 gauge theory. The electrodynamics you have studied so far can be said to respect the U1 gauge symmetry. Okay. I have told you at the level of equation of motion where it is covariant, but when you write the corresponding Lagrangian, it will become invariant. Okay, there is a difference between covariance and invariance. Invariance means it will not transform at all, remains fixed values. But here I am not talking about what symmetry you have to keep in mind. I am not making any coordinate transformation. I am making a gauge transformation. Okay. But you can have simultaneous presence of coordinate and gauge transformations. Okay, I'm not going into this immediately. If occasion presents itself, I will discuss about that. Yes. Mu I have just added because it should be transformed like a 4-vector under coordinate transformation. Just under coordinate transformation. De- না, এটা just analogy দিলাম. What I have given in the context of general relativity is given you analogy. There also you find that there is some covariant derivative occurs, and this covariant derivative occurs because the ordinary derivative of a tensor will not give you a tensor. Once you take a derivative of a tensor, ordinary derivative, it will no longer be a tensor. It will not transform covariantly under general coordinate transformation. So you modify it from comma to semicolon by inserting certain terms which are connections. So here also ordinary del mu, here I am talking about gauge symmetry, not coordinate symmetry as I emphasized. So del mu transforms as a 4-vector under covariant 4-vector rank 1 vector under Lorentz transformation. Here I am talking about special relativity. So any additional term I want to add should also transform like a 4-vector. Index should match term by term, no? So del mu, if there is a del mu, there is a mu there. So this ensures under Lorentz transformation, the whole thing transforms like a 4-vector, covariant 4-vector, or rank 1. Here, on the top of that, I'm demanding that the d mu psi transform covariant. Because once I have taken covariant derivative, this will transform covariant. Okay, so transformation property of psi and d mu psi is identical. Because psi was also transforming like this. Right? Psi going to psi prime is equal to e to the power I alpha x psi. So you see the transformation property of psi by d mu psi, the same phase factor comes when you consider the prime thing. So that's what I mean. That means whenever I want to take derivative, I should ensure that the transformation property under gauge transformation in this case, this is called gauge transformation, remains covariant. Okay. And once I do that, I get automatically the electromagnetic field coming in. So and if you can promote it to further, generalize further. Instead of U1, you can bring it the SU2, SU3 group. Then the connection you get, these are Yang-Mills connection. Yang-Mills field will come. So it is conceptually similar, but mathematics gets more complicated and physically very rich, physics-wise. The whole subject of QCD, a standard model of particle physics, is based on these groups. Okay, so the gauge principle, you will see there is a underlying theme which runs across all the models. So it will be dictated by the group you want to introduce as a symmetric group. Okay, that is not in your present semester course. If you are interested in field theory next semester, then maybe we'll talk about Yang-Mills theory. Okay. So okay. So now just for So for my rest of lecture, what I'll do, I'll choose this alpha x phase I'll choose E theta of x. Just multiplying by E, where E is the charge of an electron. I take E to be negative. So E is intrinsically negative. Okay. And for d mu, I'll write slight change in notation, this thing, del mu plus I E mu. You do the same kind of thing, analysis, you will find that if psi x going to psi prime x is equal to e to the power I d theta of x, psi x, then d mu of psi x A mu x minus e to the power I alpha নিয়েছিলাম না? I took, when I did is e to the power I alpha. I'm replacing alpha by e theta. Okay? And A also I'm changing it like this. E a mu. Earlier I wrote just del mu plus a mu. I'm changing it to E a mu. Just small alterations. Okay? Huh? D mu. Okay? Okay. So here your Dirac equation now becomes is this I d slash minus m psi, which was a del slash will be modified by capital D. Okay? And given that d mu is this will take the form I del slash minus EA slash minus R psi x. Okay? So you'll Dirac equation will look like this. Okay? So this is the Dirac equation. Will now your D has to be defined like this, no? Oh, this এটা গুণ করার কারণ হচ্ছে depending upon, suppose if I have an electron or some hypothetical particle is charged 2e or 4e, something like this, then this charge will come here as a factor. This mu will be something like, because mu has nothing to do with the particles with which the electromagnetic field is interacting. Electromagnetic field is present on its own. And the charge is another thing. This is a charge of a particle which comes in the proximity of the electromagnetic field and interacts with it. So I want to isolate the electromagnetic field part. So I multiply by, so suppose if you have a neutral particle, for example, it will not field, means E will be 0 in that case, it will not field any electromagnetic field. Okay, earlier I absorbed E and EMU, I wrote the total thing. Okay, so I segregate this into two factors. Eta. হ্যাঁ হ্যাঁ, আগের যেটা বসিয়েছি ওটা জাস্ট বসিয়ে দিলে এই রেজাল্টটা আসবে, তোমরা চেক করে নিও, প্লাস মাইনাস একটু এদিক সেদিক হতে পারে। কোনটা? ই টার্মটা, হ্যাঁ এটা বোধহয় থাকা উচিত। না, ইও থাকবে না, কারণ আমার এখানে একটা ই আছে, দ্যাট ইউ উইল ক্যান্সেল। হ্যাঁ, এখানেও একটা ই থাকবে, ই থাকবে, এখানে একটা ই থাকবে না। I have scaled both A and this thing. A also have scaled. Is it clear? না না, নেগেটিভ তো মানে ইটা বাই ইটসেলফ ইজ নেগেটিভ, ইন্ট্রিনসিক্যালি নেগেটিভ। এইভাবে লিখলাম, টু ইন্ডিকেট দ্যাট টু টেক মড ইট উইল বি পজিটিভ, তারপরে এটা মাইনাস হয়ে গেল। ইজ ইন্ট্রিনসিক্যালি নেগেটিভ, ইলেকট্রন চার্জ ইজ ইন্ট্রিনসিক্যালি নেগেটিভ। Okay, Ramsundar? Okay. So now this is the Dirac equation. You see there is a coupling of mu and psi. So it tells you how the electron is going to feel the electromagnetic field. The equation is modified in presence of the electromagnetic field. And how this modified equation is obtained? From the simple gauge principle. You elevate the ordinary derivative to covariant derivative so that the covariant derivative term also transforms covariantly. The whole equation becomes covariant under U1 gauge transformation. Okay, so this is the gauge principle which is underlying your general relativity also. There is a principle, gauge principle is there, which is a local coordinate transformation. Under any local coordinate transformation or general coordinate transformation which induce local coordinate transformation, it will remain covariant. So what happens is the local Lorentz transformation will play the role of the gauge group there. So instead of the Christopher connection, you will get spin connection. I don't know whether you have been introduced to spin connection. Spin connection পড়েছে? Okay, okay, then forget this thing. Anyway, so let me write this equation now more elaborately. So you have this thing I gamma 0 del 0 plus gamma I del I minus E slash minus M psi is equal to 0. This I have expanded this term. Okay. In fact, I can expand this term also. Minus E gamma 0 A 0 plus minus E gamma I AI. Okay. Then I multiply from the left by gamma 0. Gamma 0 square is 1. Remember, I have the Clifford algebra. Gamma nu is equal to twice eta mu nu. Right? Eta mu nu is the sign plus, minus, mostly negative. Okay, it's a matter of convention, but I am following this convention. Okay? Huh? Kunta? Oh, sorry. I gamma mu. Okay? Left multiply by gamma 0. So gamma 0 square is 1. So I have I del naught plus I gamma 0 gamma I del I. Again minus gamma 0 square is 1 A0 minus E gamma 0 gamma I AI minus M psi is equal to 0. Okay. Now gamma 0 gamma I call it, rename is alpha I. Okay, and multiply gamma, so there will be gamma 0 here. Gamma 0 is missing. Okay, and gamma 0 by itself I call it beta. So I have introduced two matrices. So my definition is gamma 0 gamma I is alpha I, and gamma 0 by itself is beta. Just renaming it, nothing else. Okay. So what happens? I have I del 0 plus I alpha I del I minus EA naught minus E alpha I AI minus beta M psi is equal to 0. Okay. So you see, the reason for writing it, recasting it like this, because I can identify I del 0 psi is equal to, so I can write I del 0 psi and take all the terms in the right, so it will become minus I alpha I del I plus E alpha I AI plus beta M psi of x. Okay. So this is reminiscent of a Schrodinger equation. Remember, Schrodinger equation was I del naught psi is equal to H psi, where H is a Hamiltonian. So here also I can identify these as the Hamiltonian. Huh? E A 0 এটা মিস করলাম নাকি EA0 plus. Okay. So this part I can identify my Hamiltonian. Now you see this minus I del I is nothing but the representation of momentum. Is that it? Hmm? Pi goes to minus I del I. Okay? Means I had more covariantly P mu is equal to I minus I no, I del mu. Right? Covariantly, remember, this is a covariant. So from here, if I put Pi, I delta I up, I can bring it down with a minus sign. On the other hand, P0 will be I del 0, same as I 0 down, because time component lowering or raising will not cost you sign. Okay? So this part I can write down as alpha I Pi, so it is just alpha dot P. Okay? Plus beta m plus E A naught plus E alpha dot A. And so the way I write it is alpha dot A, where I identify this vector A is equal to A1, A2, A3, the contravariant components. Okay. So here it occurs in the denominator, and on the subscript, I raise it to a superscript, raise it up, make it superscript, it will cost you a sign. Okay? This thing acting on psi. Okay? So this part is your free Hamiltonian. If it were a neutral particle, as I said, this term will be absent. Only this part will be there. So this is the Hamiltonian of a free Dirac particle, H naught, and this is the interaction part. So I can write this as my H naught, and this is my interaction. Okay. So H interaction is this thing. So you get exactly Schrodinger. So this is your total H psi, where the H is the total Hamiltonian. In this context, I wanted to tell you, just remind you, don't get confused. You may say that why are you bringing a Schrodinger equation, a non-relativistic equation? No, Schrodinger equation by itself is universal. It will hold even in relativistic field theory. That Cheyne must have told you when he wrote down the Hamiltonian in the Schrodinger field formulation, right? He wrote down pi is minus I del del phi, right? So you can write down so-called Schrodinger representation. You can identify the Hamiltonian there. So it is actually, it becomes the psi there is actually wave functional rather than wave function. He must have emphasized it. Input, you give a function and get a number. For function is what? Function is you give a number as an input, output is another number. But if you can give a situation where you give a function itself as an input, output will be number again. Answer like this, for example, Kala stays in Tarokeshwar. One day he comes by bus, another day he comes by train. He takes different route. So given the input root, the machine will give the distance. Okay. So it is a functional of the root. Okay. So it is a means the input is a root and output is a distance is a number. So in similar case, when you do field theory, you get a wave functional because the field there comes, field configuration comes there as an argument. You supply that, you get a number. Or better still, even in classical mechanics, when you write down the action over simple harmonic oscillator, how do you write the action? Integral dt half m q dot square minus half m omega square q square. Right? So qt function you give, after integration you will get a number. Okay? You can think of any function possible which need not satisfy Euler-Lagrangian equation, which is a special solution because under which it remains stationary up to first order. But you can in general, without bothering about Euler-Lagrangian equation, you can find any function. Okay. So given this function, after integration you will produce a number. So action becomes a functional of the function. Okay. Now Euler-Lagrangian equation comes from the fact that you consider those functions under which the action is stationary up to first order of change. That's what happens when you study the calculus of variation also, means maxima minima. At the extremal point, up to first order there is no change. Taylor's expansion, if you make f prime of f of x plus h is equal to fx plus h f prime x. The first derivative it vanishes, you say there is extremum. Maximum, minima, that is checked by higher derivatives. But up to first derivative vanishes. So up to first derivative, if you retain terms up to first order, there is no change. So similarly, that also happens with the Euler-Lagrangian equation. You determine by demanding that should be such a path that after small perturbation around that path, the action functional doesn't change. That gives you Euler-Lagrangian equation, right? So this is a functional. So that you should keep in mind. So Schrodinger equation is universal. The form of the Hamiltonian will be dictated by whether it is non-relativistic or relativistic. So here it is a relativistic system. Okay. So now, in this context, I want to tell you another thing. This pi actually comes, means is here I am talking about relativistic Dirac particle in the quantum mechanical context is interacting with some electromagnetic field. You may wonder, just try to recall how did you learn in a classical mechanics, a classical particle interacts with the electromagnetic field. Classical non-relativistic particle. How do you like the Lagrangian? Recall your Lagrangian is written like this. Half mx dot square minus e x dot a minus e phi. Phi is basically a naught, plus or minus e. Okay. This is basically the Lagrangian describing a particle, the electron, non-relativistic particle. Okay. So what will be the canonically conjugate momentum? P is equal to del L del x dot. It will be mx dot minus E. Let me put it here plus. Okay, to make it compatible. Okay. So you have the canonically conjugate momentum. So here somebody may ask you that what is the if I just write the corresponding quantum brackets, commutator bracket, then what will be? It is a background electromagnetic field. So the argument x is there. Okay? It's a background electromagnetic field. Background means it doesn't have any dynamics. Means I am not writing minus 1/4 F mu nu kind of term. Follow? It's just background. So A also depends on x. So it is a function of x. Okay? Now you see that if you write the commutation relation, you know that xi pj will be I am putting h bar is 1 delta ij. Okay. Now, what is the Schrodinger representation of Pj? It is given by just this. Okay. Schrodinger represents canonically conjugate momentum. Somebody may confuse you whether you should write minus I del I for P or for this part, which is called a mechanical momentum. This is canonically conjugate momentum and this is a mechanical momentum. There is maybe confusion. And there is a difference between these two momenta. One is that mx dot is something which you can measure exactly. Mass of the particle you know, x dot the velocity you can measure. At least classically you can measure that. Right? So this part is actually gauge invariant. All the observables should be gauge invariant. Amus are not gauge invariant because they transform mu minus del mu alpha. But magnetic field, electric field built out of it by taking curl and things like that gives you electric and magnetic field, which you have studied in electromagnetic field course, which are gauge invariant. Okay? So as far as observables are concerned, this is the mechanical momentum which is an observable, not the P's. Okay? So you may be confused. Then minus I del I, whether it should replace the mechanical momentum or the conjugate momentum. The principle is that it will always be the conjugate momentum which you define obtained by this relation. Okay, not the mechanical momentum. So here also I can write down the mechanical momentum, I can just denote it by pi plus Ca. Okay. Now, let me come to, so here also you see this P is actually some mechanical momentum plus Ea times Ea part is already there built in. Huh? Huh. It can become 0, but doesn't mean that P will become 0. Commutation bracket is between P and X, not. X with AX will be 0. Okay. So in this case, you can replace P by pi, definitely, because it will not cost you anything. But remember, these commutation relations are valid at the quantum level. Both the conjugate variables cannot be 0 simultaneously. If one becomes 0, another becomes uncertain. You have to satisfy uncertain relation. Okay. So here also you see these things, the same combination comes. Alpha dot P minus alpha minus E alpha dot A. So I can write down this thing alternately as alpha dot pi plus beta m plus EA naught. Plus P minus EA, that we can write as mechanical momentum. In the same spirit. Okay. I just defined it like this. So now let us try to use. Do you want rest? Okay. I'm going very slow. Huh? Anyway, let's see. বেশি স্লো হয়ে যাচ্ছি না তো তোমাদের জন্য? হ্যাঁ, কৃষ্ণা তুমি বলো তোমার অভিমত। আমি এক এক সময় মনে হয় তোমরা কিছু বলছো না, হচ্ছে বোর হচ্ছে বোধ হয়। এমনিতেই তোমরা ক্লাস ঠিক আসো না, ভাবছি তোমাদের বোর করি নাকি। হ্যাঁ, প্রশ্ন থাকলে করো।
যে ল্যাগ্রেঞ্জ ইকুয়েশনটা ছিল ক্লাসিক্যালের
নন রিলেটিভিস্ট, নন রিলেটিভিস্ট।
নন রিলেটিভিস্টিক, এবার যদি আমি এখান থেকে পি বার করে এটা পি ক্যানোনিক্যালটা পেলাম, ক্যানোনিক্যাল টার্মটা পেলাম। এর মধ্যে এই টার্মটা হচ্ছে মেকানিক্যাল টার্ম আর এটা ইন্টারাকশন টার্ম। এবার স্যার এটা তো আমরা ক্লাসিক্যাল নলেজ হচ্ছে শিক্ষার ক্ষেত্রে এটা পাই,
ক্লাসিক্যাল না, কোয়ান্টাম
লেভেল আমরা এটা পাই। এবার কি একটা বললেন না জিরো হয়ে গেলাম, ঠিক ওই জায়গাটা বুঝ ধরতে পারলাম না।
নো বলছিল যে পিটা যদি জিরো হয়ে যায় তাহলে তো দুদিকে জিরো হয়ে যাবে।
এটাও জিরো বলছিল।
হ্যাঁ, না এটা বলছে যে তুমি এখানে যদি পিটাকে যদি মেকানিক্যাল মোমেন্টাম দিয়ে রিপ্লেস করো, মানে যেটা পাই যদি লেখো, এখানে পির জায়গায় পাই লেখো, তাতে কোনো ক্ষতি হবে না। কনজুগেট মোমেন্টামটা একই রিলেশন স্যাটিসফাই করবে। কারণ কি এখানে তো এক্স আর এখানে এর মধ্যে এক্স আছে না, ফাংশন অফ এক্স, এটা ইন্ডিপেন্ডেন্ট ডাইনামিক্যাল ভেরিয়েবল।
তখন স্যার মানে আপনি বলছেন এদিকে এটা এক্স হবে আর এক্স সামথিং এক্স এর কিছু একটা ফাংশন হবে।
হ্যাঁ হ্যাঁ, তো এক্স এক্স নিজের কমিউটেটর জিরো
হয়ে যাবে।
হ্যাঁ,
মানে
এবং এটা হচ্ছে যখন এটা ব্যাকগ্রাউন্ড আছে বলে। এটা যদি ডাইনামিক্যাল হতো তাহলে এই এক্স যে ভিতরে বসে আছে ওটা তুমি এ ফাংশন অফ এক্স ঠিক ওইভাবে ধরতে পারতে না, ওটা তো কন্টিনিউয়াস ডিগ্রি অফ ফ্রিডম।
পিটাকে তখনই শুধু ফাংশন বলবো যদি এই পার্টটা আমার জিরো হয়, নাহলে তো কি করে বলবো?
না এই পার্টটা না না, এই পার্ট কেন জিরো হবে? পিটাকে মানে কমিউটেটরের মধ্যে, তোমার এই কমিউটেটরের মধ্যে তুমি পিটাকে লেখো না এক্স আই পাই জে প্লাস ইএআই, এক্স আই এর সঙ্গে এই কমিউটেটরটা জিরো হয়ে যাবে।
আচ্ছা হ্যাঁ,
তখন এক্স আই পাই জেটা তোমার ডেল্টা আই জে দেবে।
আচ্ছা আচ্ছা ঠিক আছে। তুমি মেকানিক্যাল মোমেন্টাম আর ক্যানোনিক্যাল মোমেন্টামটা একবার বলবে কোনটা অবজারভেবল বুঝলাম না।
মেকানিক্যাল মোমেন্টামটা অবজারভেবল,
যেটা অবজারভেবল এটা হচ্ছে ইন্টারঅ্যাকশন টার্ম।
কারণ এটা তুমি অবজার্ভ করতে পারো। ভেলোসিটি একটা পার্টিকুলার, ক্লাসিক্যালি বলছি, ইউ ক্যান মেজার ইট, পজিশন জানো, ইউ ক্যান মেজার ইট, মাসও জানো, মেকানিক্যাল মোমেন্টাম তুমি জানো। তো পিআইটা তুমি এরকম মেজার করতে পারো না,
কারণ আমি ইন্ডেক্টর বিজ্ঞান এটা করতে পারবো না।
হ্যাঁ এইগুলো নিজে মেজার করা যাবে না বলে।
হ্যাঁ ঠিক আছে। আর ও যে প্রশ্নটা করলো ওটা বুঝলাম না, জিরোটা ওটা জিরো জিরো হচ্ছে মানে ধর এই পিটার জায়গায় পুরো লিখি। হ্যাঁ এক্স ফাংশন অফ কি আছে, পাই আছে আর হচ্ছে এটা আছে, এক্স এর সাথে এ তখন কি হবে, এ তো এক্স এর ফাংশন, এই তো এক্স এর ফাংশন কারণ ব্যাকগ্রাউন্ড বলে কমিউটেটরটা কি হয়ে যাবে, জিরো হয়ে যাবে। তাহলে এক্স আর পাইটা ডেল্টা আই দিয়ে দেবে, ঠিক আছে? প্রোডাক্ট ছিল,
হ্যাঁ,
পজিটিভ ছিল, সেটা পরে নেগেটিভ কিভাবে হলো?
ও এআইটাকে আমি উপরে উঠিয়ে দিয়েছি মাইনাস সাইন করে, আর থ্রি ভেক্টর এ যেটা, ওটার উপরের কম্পোনেন্ট গুলোকে আমি আইডেন্টিফাই করেছি এই ভেক্টরের তিনটা স্পেশাল কম্পোনেন্ট, নিচের গুলো নয়। আমাকে তো ডিক্লেয়ার করতে হবে আমি নিচের গুলোকে আমার থ্রি ভেক্টরের কম্পোনেন্ট বলছি না উপরের গুলোকে বলছি। আমি সেই কনভেনশনে কাজ করছি যেটাতে উপরের গুলোকে আমি থ্রি ভেক্টরের কম্পোনেন্ট বলছি। কৃষ্ণ কিছু বলবে? হ্যাঁ, ক্লিয়ার আছে সব? হ্যাঁ, বুঝতে পেরেছো? এগুলো হয়তো তোমরা জানো অনেকটাই, তবু আমি রিক্যাপিচুলেট করলাম কারণ পরবর্তী পদক্ষেপে এগুলো কাজে লাগবে আর কি। একটু সময় নিলাম, বোর হলেও একটু শুনে নাও আর কি। ঠিক আছে, সবাই এসে গেছো? Okay, so now what I'm going to discuss is Heisenberg equation of motion. Okay, I have got the identified the Hamiltonian, the total Hamiltonian is given like this. So I need to calculate the equation of motion of these observables. Remember, any observable, take any observable, its equation of motion is given by d this term is important in the case where it has got explicit time dependence. Otherwise, it will have implicit time dependence. That means it will have contain arguments which are in turn time dependent, not directly time dependent. In that case, only the first term will contribute. But if both the types of term are present, then you have to consider both the terms. Okay. So let's try to calculate the commutation this dxi dt. First example. Position variable. Then okay. But xit doesn't have any explicit time dependence. Okay. So this term will not contribute. Regarding H, I have both the free term as well as the interaction term. Okay. So I can just write it as I alpha dot p plus beta m plus E A naught minus E alpha dot A. না আমি যেটা বলছি যে x has got an implicit time dependence. Means x, okay, means x depends on time, but here this bracket will give you commutation relations between the phase space variables themselves. This in general will be some any phase space functions, okay, built out of x and p's, phase space functions. So these phase space functions will have time dependence through x and p. These are called implicit time dependence. This function, if apart from having x and p, it has got another time dependence on its own, then I call it as explicit time dependence. So whatever time dependence of just xi is concerned, it will be obtained only from the commutation relations. Okay, just from the commutator bracket. Okay, so now you calculate, what do you get? This xi, when you calculate the bracket, it will look from terms here where it is conjugate to, which is conjugate to xi. You know the only conjugate variable is momentum, which occurs here. It doesn't occur here, it doesn't occur here, it doesn't occur here, because they are independent of p. So as far as this commutation bracket is concerned, these three terms will not contribute. Okay. So you can forget these three terms. All these terms. Okay. So you will have is equal to I alpha dot p xi. Okay. Okay. So what do you have? Alpha dot p I have identified. The p's are the components. So it is, I have to write xj, pj, xi. I have to use a different dummy variable here. Is that it? Xi. Okay. So this I xj sorry, alpha j. What I am doing. Alpha j pj xi. Alpha is a matrix, so it will not contribute to the commutation relation. Only Pj Xi. Xi Pj was I delta j. So Pj Xi will be minus I delta Ij. Okay. So this will make it minus I plus I 1, so it will become just alpha I. So Xi dot can be identified equal to alpha I. That's why this operator alpha I was gamma naught gamma I, right? This operator can be identified with the velocity operator. Okay. So now I give you a homework. Consider the second observable. Second observable will take it to be pi I, mechanical momentum itself. So I give it as a homework. Kala, you note it down. Show that d pi I dt, this is equal to, you see here, you should be careful. Explicit time dependence will occur. Whereas pi I is pi minus ai. Ai is changing with time. Okay, because you don't know the background magnetic electromagnetic field may be time dependent. Okay, so you should keep that term and then run through the commutation relations. It's not difficult. Ultimately, you will find that means you should, let me write it in compact notation. D pi I is equal to E plus alpha plus B. This is the Lorentz force. Alpha is the velocity operator. So you can derive from Heisenberg relation this thing. It's a bit long, but it's not difficult. Please do it. Okay. Where E's and B's, I define it like this. Okay. Remember the A's I defined, the vector A's are A1, A2, A3. This is minus of A1 minus A2 minus A3. So don't confuse. This is my way of doing writing things. Okay. So let me try to extract some physical significance of this Dirac equation, physical. And how do I do it? I go to my familiar regime, non-relativistic situation. We are still in quantum mechanical level, but non-relativistic. Okay? And then we'll be able to see what are the changes are occurring, which are purely relativistic effect and which are not relativistic effect. Okay? So, so we start with this equation itself. But before we start, remember psi was a 4-component spinorial wave function. I split it into 2 components in the following manner. Right? Psi is equal to phi and chi. Phi is a 2-component. This is also 2-component. As a whole, 4-component. I rewrite this equation. And I have defined alpha and beta for you. Beta was simply gamma naught, and that was gamma I. You can take their product and rewrite this equation in terms of phi and chi. You can easily show, again I am leaving that as an homework. This is simple, just substitute the matrices. Okay? You can show that this, you get this pair of equations. Homework, show that this equation boils down to the following pair of equations. I del phi del t is equal to sigma dot pi plus m plus pi chi I. Okay. This is the pair of equations you will get. It's not difficult to show. Are you following the line of logic? You just substitute it here. Alpha, gamma, all the ingredients are given to you. Now just compare.
স্যার ওই সিগমা ডট পাই তারপরে ওটা কি কাই লিখেছেন ব্র্যাকেটের পরে প্রথম ইকুয়েশনটা?
হ্যাঁ কাই
আচ্ছা ঠিক আছে।
কাই প্লাস m plus e naught phi sigma dot pi phi plus e naught minus m chi. Okay. Now I want to go to the non-relativistic limit. You should be very careful about the non-relativistic limit. You must have studied, again I am in your BSc, but still I think that it is worth reminding you that energy of a relativistic particle is given by gamma m, right? C I'm taking to be 1, but if you means let me put C, gamma m C square. Okay. So what it is? MC square by root over 1 minus B square by C square. Okay. So this is the energy. So what it is? You can take a binomial expansion, B square by C square to the power minus half. So you will get MC square 1 plus B square by 2C square plus higher order term. Okay. Means it will be C to the power, means higher order term C to the power 4 or something like this. Plus dot dot dot, all sorts of terms. So what I want to emphasize to you is that the first term is MC square. And second term gives you precisely half mv square. And then there will be C square or something like of this order term, higher order term. Okay. So what in non-relativistic situation, what we do, you see, if you just take blindly C tends to infinity, it will diverge. Is that it? So what you say no, I'll forget the rest mass energy. Over and above that will give me the energy. This is a free particle energy. So you subtract that from E, mc square, and then take the limit C tends to infinity. Then only this term is C independent. It will survive. Other terms will vanish. Okay. So that way you recover your non-relativistic limit. But it is important to subtract the rest mass term right from the beginning and then take the limit C tends to infinity. I hope you knew that quite well. So here also I should be careful when I write the phases and things like that. In relativistic situation, the phases will have typically ET kind of term, right? For example, field mode expansion, you did e to the power minus I k dot x. K dot is omega kt plus 3 vector k dot 3 vector x. Omega k is the relativistic energy of kth mode, right? Means with momentum k. So that energy contains the rest mass energy. So in order to facilitate your definition, your taking of your or extra facility the process of extraction of a non-relativistic limit, you have to extract that out, the rest mass term, and retain the rest other terms. So rest mass term has to be subtracted out. So this is the basic principle. So understand. So with this, I'll do this the following. I'll write non-relativistic limit because I'm working in C tends to C equal to 1. So my MC square will be just F. Okay. So to study non-restricted limit, set phi is equal to e to the power minus IMT phi, and chi is equal to e to the power minus IMT x. Okay. So time dependence will be maximum here with the rest mass because it is a highly energetic. The particle is non-relativistic. So whatever extra phase and at this thing are these slowly varying phases. Compared to the rest mass energy, it will be much smaller. So these two phi and chi slowly varying functions of time. Okay. So once you substitute it, then you just substitute here. Okay. Carry out some simplifications. And you'll get the following pair of equations. Again, this is a homework. Show that in terms of the above pair of equations reduces to the following. Okay. You will get this. This 2m, you see this term 2m is will come, there are two sources. Once when you differentiate with respect to del t, this 1m terms will come. And there is already 1m term occurs here, so they will add up and to give you minus 2m. আমি যেটা আগে বললাম যে I have taken out the time dependence part of these functions. I have taken out the rest mass term, extracted out. This is the rest mass term. Okay. বুঝলে না তুমি যখন ক্লেন গর্ডন করেছো বা শোরিঞ্জার ফিল্ড থিওরিতে করেছো, তখন শোরিঞ্জার ফিল্ড থিওরিতে কি করেছো? পজিটিভ এনার্জি সলিউশনস গুলো রেখেছো, হ্যাঁ, অন্যটা নেগেটিভ এনার্জি সলিউশন আসেনি, তাই তো? নেগেটিভ এনার্জি সলিউশন গুলো অটোমেটিকলি সাপ্রেস হয়ে যায়। ইউ হ্যাভ সিন there is a limit of ক্লেন গর্ডন ফিল্ড, হ্যাঁ? So only positive energy solutions are kept. The positive energy solution comes with e to the power minus I k dot x. With, right, a annihilation operator times e to the power minus I k dot x. So minus I k dot x, if you expand, you will get e to the power minus e t plus I k dot x. Minus I e t, that gives you the total time dependent phase. But E consists of the rest mass and other kinetic energy. Kinetic energy part is very small, half mv square compared to the rest mass. So rest mass I have extracted out, mc square. in my C equal to 1 unit, this is just m. So whatever is left behind will be very slowly varying function of time. Is it okay? So these are the two equations you will get. Please derive it. Kala, you note it down and make circulate to all of them. So now I am further assuming that the strength of the electromagnetic potential is very weak, is very small. So yes. So in other words, this EA naught is very, very less than 2m. This is the electrostatic energy is very, very small compared to the rest mass energy. So what will happen? This pair of equation will look at. If you look at these equations, you will find, just a minute. I have already told you this is slowly varying. So I am working in an approximation where del x del t is close to 0. Okay, very small. And this is also very small compared to this, to m. Okay. So I'll have basically means and del x del t also very small, and therefore in this approximation I have sigma dot pi phi almost equal to 2m x. In other words, x is equal to sigma dot pi phi by 2m. This is an approximate solution. Okay. M being the rest mass and pi is the mechanical momentum. So momentum, again mechanical momentum non-relativistic, it will be very, very small compared to the rest mass, right? So this as a whole will be very, very small than phi. So this x which occurs here in chi is approximately given by, means is much smaller than this phi, which occurs in this small phi. And remember, this phi was the upper component of the Dirac spinor, the way you have written, and this is the lower two components. So it shows that upper components, lower components is much, much smaller than the upper two components. That's why the upper two components are called large components, and lower two components are called smaller components. And this is valid only in this approximation. not otherwise. Okay, but we want to see what happens in this approximation, because most of the time our life is spent with the non-relativistic scenarios. Okay. Now, if we just substitute this in one of the, so now this x I can substitute back here. Okay. So I'll get what? I'll get x is sigma dot pi by 2m, and this sigma dot pi is already there, so it will give me sigma dot pi whole square by 2m phi phi plus E A naught pi. In other words, I can just write down these as. So what do you get? You get a Schrodinger-like equation involving the upper two components of the Dirac spinner. I del phi del t is equal to again some effective Hamiltonian in this approximation acting on phi. Is not it? You get an effective Hamiltonian valid in this regime. Okay. So this can be regarded as a generalization of Schrodinger equation, and in this scenario. Okay. Now we need to actually evaluate this sigma dot pi. What is sigma dot pi? Square. Okay. Sigma dot pi square I can write down as this thing, sigma I pi I is sigma dot pi, another is sigma j pi j. Okay. Now for sigma I, sigma j, I can write as a commutator and anti-commutator. This has half sigma I, sigma j commutator plus half anti-commutator, sigma I, sigma j, pi I, pi j. Okay. And this is nothing but your Lie algebra, SU2 Lie algebra generators. Remember, sigma I satisfy SU2 Lie algebra. So this sigma I, sigma j is equal to 2I epsilon I j k sigma k. And these are nothing but, I remember when I introduced the Dirac operator for the plane, I introduced the Clifford algebra there. So this gives you twice delta ij identity, two-dimensional identity. Unit matrix 2 by 2. Okay. So these two will cancel and you will be left with I epsilon I j k sigma k pi I pi j plus delta ij will make it pi square and I2. Okay. But remember, pi I, pi j, you may think that, oh, this is symmetric, this is anti-symmetric, that will collapse. This is not true. The pi's which were I del I, the ordinary derivatives, they commute. There is the ai's terms there, so they will not commute. Do you follow? So you should be careful. You should not blindly apply means. So you should be careful why pi had this role minus I del I means it has to be, but not the mechanical momentum. Okay. So you should write it as again, since it is antisymmetric, you should write symmetric part as well as antisymmetric part. Symmetrize and antisymmetrize. But after you symmetrize it, means pi I, pi j plus pi j, pi I, that will be symmetric by construction. Okay. That will vanish. But there will be pi I, pi j commutator term will be there, which will be antisymmetric by construction. So that will survive because that will not vanish. So I by 2 epsilon I j k sigma k pi I pi j plus pi square. And just I2 I am not writing. Okay. So now I have to calculate pi I pi j. Okay. Let me erase it here. Both are special indices. So I can write it as pi I pi j. Special indices, there are 2 of them, so it will cost you no sign. And this is equal to pi minus EAI, right? And this is pj minus EAJ. Okay. Pi, pj commutator will vanish now because they are del i's up to a sign factor y. But pi ej, so it will be pi minus epi aj minus eai pj. And then there will be commutator ai aj. AI is a function of x, x commutes among themselves, so ai aj also will commute among themselves. Okay. So only these are the surviving terms. So I can flip the sign here, right here, pj I bring it here, ai take it here, pj I. Okay. What is PIAJ? PIAJ is can you tell me what is PIAJ? You have PI XJ. What it is? Minus I delta IJ. Right? Which you can write as minus I delta I xj. Is that it? So here, instead of x, you will have aj because this is a function of x. So minus plus I e del I aj. Okay, plus I e del I aj. And this will be, this is minus sign was there, so there will be minus I e del j ai. Okay, and then I can write down this as I e I e del j ai ai minus del I Aj. Okay. This is nothing but I E. This is del Ji. According to our notation, you can check that this will turn out to be epsilon this is F Fji, which will be I E epsilon I j k b k. Isn't it? So now you can see that these bk's are three vectors. I don't bother about whether this indices are up or down. Okay. And so with this, I can substitute it here, and you can see again, just do few steps. I'm already shoot my time. It will give you minus pi square minus E sigma dot B. Okay. Homework. I've done essentially all the steps. Just fill up the few lines, gaps. Okay. So what happens? Your Hamiltonian, this is a Hamiltonian. So this Hamiltonian becomes now, if you call it the Hamiltonian H, the equation becomes I del phi del t is equal to sigma dot pi square is this. So you will get pi, I now write in terms of p minus E a whole square by 2m. And minus E by 2m again divided by sigma dot b plus E a naught. This is our Hamiltonian acting on phi. So you see this is a term sigma dot b. This is a new result, is actually inherited from the actually relativistic structure of the equation. Why it is important? Because sigma, I told you in my group theory class earlier that what spin does, in order to incorporate spin, you necessarily have to talk about multi-component spinors, right? Whenever there is a mixing of these components, you get spin. And this is precisely the mixing it does, because phi contains now two component spinor, right? Now, sigma dot, this thing mixes, the other terms don't mix. They leave the top components of phi and the bottom components of phi undisturbed. They just act individually. But these terms, sigma dot p is a polymatrix, 2 by 2 matrices. All three of them are present here, depending on the direction of B. If B is in the Z direction, then of course, it's a trivial thing. Sigma 3 will only come. But otherwise, it will mix them up. So this is the spin dependent part. So it shows that spin dependent occurs in the magnetic interaction. So only if you have particles with magnetic moment, only then you get this kind of coupling. So identify this as your magnetic moment term. So automatically electron not only has got its spin, it has also got magnetic moment. You follow? So all these aspects are explained by Dirac equation. Shown that this particle which obeys this equation has necessarily has spin half as well as endowed with some magnetic moment. And this magnetic moment, you can recall your atomic physics class, I think Partho has taught you. हाँ शेष আমার জাস্ট 2 লাইন বলি শেষ আমারও টায়ার্ড হয়ে গেছি 2 লাইন বলি শেষ লাস্ট এ You recall your magnetic interaction term. Your magnetic, if I restore a magnetic interaction term, is given by minus EH bar by 2mc sigma dot b. This is the magnetic interaction term. With this thing is, you call it mu dot b. This is the magnetic moment, right? I've inserted H bar and C now, and that can be easily done. So far I have been working with your unit H bar C all taking to be 1. But if you want, you can reinstate them. Just simple dimension analysis will do it. Okay? And once you do that, you can see that the coefficient of B comes to be this object, you call it magnetic moment. Okay, this magnetic moment and mu is here EH bar by MC S. S is sigma by 2. Okay. Let me write it as these things. Twice 2mc. Take common. Instead of sigma, I write 2s. That's the way you write s equal to sigma by 2. Right? Huh? Generally, so here we get 2 as the gyromagnetic ratio. Huh? পার্থ পড়িয়েছে তো এগুলো হ্যাঁ আচ্ছা যাই হোক আজ এ পর্যন্তই থাক কিছু কোয়েশ্চেন অনলাইনে জানি না কেউ আছে কিনা আমি বুঝতে পারি না যাই হোক ওকে ওকে এনি কোয়েশ্চেন আমি আবার মঙ্গলবার দিন আসবো 2:30টার সময় আমি নেব ওকে ওকে আবার একটু সাহায্য করে দাও এটা হ্যাঁ 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 না 5 কি 2 কম্পোনেন্ট অবজেক্ট না সিগমাটা তার মধ্যে উপর নিচ কম্পোনেন্টকে মিশিয়ে দেবে মিশালেই মানে এটা স্পিন হয়ে গেল ঠিক আছে না